Welcome to graph theory. This is a completely introductory video on graph theory. This is not the graphs that you see in pure maths with kind of bar charts or anything like that, or XY plots. It's nothing like that. This is decision graph theory. And in this video, I'm going to be introducing lots of definitions and illustrations and some notations. Yeah, there's lots going on in this video. Okay, so what is graph theory? Well, let's consider what is a graph. Graphs, unlike graphs that you probably met before, graphs in this sense contain lots of lines and dots. So these are decision graphs. We might have some dots which are not connected. So we'll explore a little bit in the video. So this is an example of a graph. And a graph is made up of two objects. We've got something called a node, or sometimes called a vertex. Okay, these two words can be used interchangeably for this course. And we also have the arcs, or the edges. Okay, these are the lines which connect the nodes together. Okay, I've filled in a node there, but these are all hollow nodes. Doesn't matter. Sometimes the nodes will even have letters in them to kind of distinguish between them. That's fine. It is very much just zero-dimensional objects and one-dimensional objects all joining together and producing graphs. Okay, so let's crack on with lots of kind of definitions of graph theory. Okay, so here we have a graph. It's got nodes labelled A to G, and it's got a variety of different arcs on there. And I want to define a number of definitions for you. So notice that this arc here, this arc is an arc that has joined a node to itself. That can sometimes happen in a graph. When that does happen, we refer to it as a loop. Okay, a loop. It is an arc that connects a node to itself. Don't get confused between loops and cycles. This is not a cycle. Well, it is a cycle, but loops are always cycles, but cycles aren't always loops. Cycles are paths which move around the graph such that you get back to where you started. So this is an example of a cycle in this graph. So to denote this cycle, I could refer to it as D, E, B, C, D. Hold on. D, E, oh, I missed the A. D, E, A, B, C, D. There we go. So that is how I can represent this cycle in this graph. Can you spot any other cycles in this graph? There is one, or a few particular ones. Let's go this way, and then up there, and then across up there, down there, down there. Let's go down to G, and let's go back to F. So I'm going to label this one A, B, C, D, G, F, E, A. This is a cycle, but this is a particular type of cycle. This is called a Hamiltonian cycle, and that is because this cycle visits every node. Okay, it visits every node exactly once. So therefore, it is not just a cycle; it is a Hamiltonian cycle. Okay, a few other things about this graph. There's something called the order or the degree of a vertex, which is a measure which is used for a variety of different reasons. And essentially, it counts how many arcs are connected to each node. So this is a number that is assigned to every node in a graph. So, for example, looking at node A, we can see there are 2 arcs connected to it. So the order or degree of node A is 2. Again, these two words are used interchangeably. There's quite a few instances where there's 2 words for the same thing in graph theory. There's 1, 2, 3, 4 arcs attached to B. C, there's 1, 2, 3, so that's got an order of 3. 1, 2, 3, 4 attached to E, 2 attached to F, 2 attached to G, and there's 4 arcs attached to D. However, it has order 5 because we do count this twice because it's connected there and connected there. So it's more about the number of connections rather than excuse me, rather than the number of arcs. Okay, so those are the orders of the nodes. Now, what you may notice is each arc or each edge contributes 1, 2 orders to the graph. So therefore, if you add up all of these orders, it has to be an even number. Okay, so if you sum all the orders of the nodes, that must be an even number. And this idea is referred to as the handshake lemma. And the reason for it is because every arc contributes to the orders. So specifically, the even number is going to be 2 times the number of arcs in the graph. Okay, so we've looked at loops, cycles, Hamiltonian cycles, order and degree of a vertex, and the handshake lemma. It's one other thing I want to introduce you to before moving on to some other definitions, and that is isomorphic graphs. So an isomorphic graph, or isomorphic graphs, these are isomorphic because actually we don't care about the shape that they produce, we care about how the nodes are related to each other. What I mean by isomorphic is these graphs are exactly the same. They are exactly the same. It's not that they are slightly different or look different, they are exactly the same because we don't care about what they look like, we just care about the topology. How are they connected? How are the nodes connected to one another? So what let's just illustrate a little bit for you as to why these are isomorphic. Why are these identical? This node here connects to all 4 of the other nodes, and this node here in this graph also connects to all 4 of the other nodes. And then from there, we have a triangle that goes that way, which we can represent as that one. And then we also have a triangle going the other way, which we could represent as that one. So these 2 graphs are completely identical, and we refer to these as being isomorphic. They represent the same information in terms of graph theory. Okay. All right, on to page number 3 then. Here I have 6 graphs. And what I'm going to do is I'm going to define for you a number of terms, and then I'm going to look at these 6 graphs, and we're going to decide which graph satisfies the definition that we're looking at. So let's get started. Connected is the first one. Okay. Now, by definition, a connected graph is a graph which you can get from any node to any other node by just using arcs. Okay. So, for example, here, I can get from this node to this node, or this node to this node, or this node to this node. I can get from any node to any node just by using arcs. So therefore, A is connected. B, however, is not connected because I've got this bit over here. If I start here, I can't get to any of those 3, and if I start on one of those 3, I can't get over there. So this is not a connected graph. Similarly, this is not connected. This is connected, this is connected, and this is also connected. Okay, so it's just B and C. And in fact, just going to modify B slightly. I'm going to introduce another node over here and do that, just to illustrate that it doesn't have to be one lone node by itself. You could have a pair separated, or maybe even another node over there which does that. Again, that is still a disconnected graph because this is not a node. I can't jump from this node down to this node, but I can get through there, I can get through there, but I can't get from these three to these three, so therefore this is a disconnected graph. Okay, so A was connected, D is connected. Okay, I can get from here to here, I can do that route, or to get from here to here, I can do that route. This is connected, and this is connected. So A was connected, B was not, C was not, D was connected, E was connected, and F is connected. All right, the next one is simple. So a simple graph is a graph which does not contain any loops and has at most one arc between any pair of nodes. So C is not simple because we have a loop. F is not simple because we've got two arcs between those two nodes. The other four are simple because there are no loops and there are no pair of nodes which has more than one arc between them. So it's just C and F which are not simple. A, B, D, E. Simply connected is a definition which means that they are both simple and connected. So if any graph has the top two lines which are ticked, then this line is also ticked. B is not simply connected because it's not connected, and F is not simply connected because it's not simple. Okay. A complete graph. This is a graph where every node is drawn, has an arc to every other node, okay, directly. It also doesn't contain any cycles, doesn't contain any loops, and doesn't have more than one arc between any pair of nodes. So this one is a complete graph because every node is connected directly to every other node. B is not, C is not, D is not because I can't connect these ones, they're not connected, so that's not a connected graph. E is connected because every node is connected directly to every other node, and F is not connected. It's not complete. So A and E are complete. A and E, and these have special notations. We refer to this as K3, and we refer to this as K5. Okay, so this is complete graph 3 and complete graph 5. And in a minute, we're going to have a look at how many arcs each of those would have, and then in general. Okay. Next definition is a bipartite graph. So a bipartite graph is a graph where the nodes can be split into two distinct groups such that a node is not connected directly to a node in that group. Normally, bipartite graphs are laid out like D has been laid out. There's one group here, and there's one group over here, and we can see that all of the nodes in the left-hand group do not connect to each other, and all of the nodes in the right-hand group also do not connect to each other. So therefore, this is a bipartite graph. This is not bipartite because I can't split them into two groups. If I take this one off, then those two are in the same group and connected, and I can do the same thing with the others. So that's not a bipartite graph. This is a bipartite graph. A little bit harder to see, but let's say I put the middle ones, so we can see it's essentially just 2 3s, isn't it? So if I put the middle ones on one side, and then I put the outer ones on the other, and this graph is isomorphic to this graph. These are the same graph. Okay, and we can see that now that's clearly bipartite because these two are in one group and don't connect to each other, and these four are in the other group and don't connect to each other. Okay, so therefore this is a bipartite graph. C is not bipartite because it's got a loop. Okay, it's a node. A node is connected to itself, so therefore it can't be bipartite. We already said that D is bipartite. E cannot be bipartite because it's a complete one. The only complete graph that is also bipartite is K2, or K1, I guess. And F is bipartite actually, because this node. Oh no, it's not bipartite. Hold on. yes, this node does not connect to this node, so we can put those two in the same group, and this node does not connect to this node, so we can put those two in the same group. So it is a bipartite graph. It's not laid out like this, so it's not quite as obvious, but F is bipartite. So that's B, D, and F. B, D, and F. Okay. The next one is a digraph. Okay, this is a contraction of two words, directed graph, and those are graphs which contain arrows. So sometimes you'll come across graphs where arcs can only be followed in one direction. So that is clearly C and F. The others are not digraphs. It only needs one arc to be a directed arc to be referred to as a digraph. It doesn't have to be all of them. Okay, if it's got one or more directed arcs, it is a digraph. So that is just C and F. And then finally, a complete bipartite. Simply connected was ticked if simple and connected was ticked. Complete bipartite is not ticked just because complete and bipartite are ticked. So that's not what this means. A complete bipartite graph is a graph which is bipartite and has as many arcs as possible, keeping it simple. So this one here, which is bipartite, there can be no more arcs added. So you can't have any loops, otherwise it wouldn't be bipartite. And if you add two, then it wouldn't be simple. So therefore wouldn't be complete. So this is classed as a complete bipartite because every node in one group is connected directly to every node in the other group. So it's not a complete graph because these three nodes aren't connected together and nor are these two, but it is a complete bipartite graph. So D satisfies that. This one is clearly not complete bipartite because you would need those arcs and those arcs. And F is also not complete bipartite because you've got two arcs there, so it's not simple. Okay, so that's those definitions there. If you have any questions on those, please just pop a comment in the bottom and I'll get back to you on those. I hope I've been as clear as I can in my explanations of them. You do need to know those definitions for the modelling with algorithms course. Okay, and before we look at trees, which is the last page for this video, I want to look at arc counts. So we're going to have a look at the complete graph, and we're going to have a look at the complete bipartite graph. Okay, so the complete graph, we've got two here. We've got K3 and K5, but you can have Kn, which would have n nodes, and every node is attached once and only once to every other node. How many arcs are there going to be? Well, for K is 3, we've got 3 arcs. For K is 5, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 arcs. And you may have just picked up there how I counted those. I've chosen a node to start with, and then I've got 1, 2, 3, 4 that are connected to it. So obviously one less than n. And then this one here, I move round to the next node, and then we've got 1, 2, 3, 4 attached to it again. However, one of them has already been counted. So I've only got 3. 1, 2, 3. And then I can move on to this one, and then 2 have gone, so I need to count 2, so that's plus 2. And then finally move to the last node here. 3 have gone, and there's only 1 left. So it was 4 plus 3 plus 2 plus 1. Another way to think about it is I've got 4 connect to every node, so 4 times 5 is 20, and then because I've counted each one twice, each arc twice, then you half it, so 20 over 2. But essentially, Kn has the n minus 1th triangle number of arcs. So the 4th triangle number is 10, so K5 has 10 arcs. The 2nd triangle number is 2, so therefore K3 has 2 arcs. In general, the complete graph will have half n times n minus 1, which is the n minus 1th triangle number. Okay, n minus 1th triangle number. The other way to look at it, as I mentioned shortly ago, there are 5 nodes, and each node has 4 arcs attached to it. So that is n times n minus 1. In doing so, you're counting each arc twice, so therefore you need to half it to get the number of arcs. Okay. So that is how many arcs the nth complete graph will have. And then the complete bipartite graph, this one's going to have 1, 2, 3, I don't know, n nodes in one group, and then in the other group, it's got m nodes. If I consider this node in the left-hand group, it's going to have 1, 2, 3, 4. It's going to have m arcs on it. And this one's also going to have 1, 2, 3, 4. It's also going to have m arcs on it, as is that one, m, and so on. And every node in this group will have m arcs, and there are n of them. So the total number of arcs of this graph then is going to be n times m. Okay. N times m, where n is the group size of one of the partitions, and m is the group size of the other. Okay, right, that finishes this page. One final type of graph I want to consider, and that is a tree. So a tree is there's a few definitions of a tree. We're going to define this as being a simply connected graph which has no cycles. Okay, a simply connected graph which has no cycles, or you could define it as a simply connected graph with n nodes and n minus 1 arcs. Okay. So for example, if I have that 3 nodes, I'll have 2 arcs, and I could either draw those 2 up, or I could have drawn those 2 up, or I could have drawn those 2 up. That is the only tree with 3 nodes. With 4 nodes, 1, 2, 3, 4, some options now. I can either have them all in a long line, or I could have kind of a root node, which connects all the others. So these are the 2 trees that you can have with 4 nodes. Notice that in each case they are simply connected with 3 arcs. Okay, so it fits this definition here. Similarly, they have no cycles. Okay, you're not going round. You can't go round. And they're called trees because that's exactly how trees grow. Branches. They don't tend to go back in on themselves. Although I know that can happen, but naturally, ideally it doesn't. And then when you get to 5, well, you start getting all kinds of options. So you could have one kind of master node, again one root node, or you could have one long line, like that, or you have this intermediary one, which has a 2 and a 1 and a 1. So you could have that. So these are the 3 trees which have 5 nodes. There are no others. There's only one tree with 2 nodes. That is just 2 nodes connected. There's only one tree with 1 node. Yeah. So any graph that satisfies either of these conditions is a tree. And in fact, these 2 conditions, they are, if one is true, the other is true. Okay. Yeah, all right, so I think that's all the definitions of graphs. I know it's been quite a long video. There's lots of kind of graph terminology and notation and things that we've looked at. All of it you need to have in your mind as we go through, not just the graphs and networks section of this module, but everything for this module. Okay, these words will be thrown about and used all the time. All right. Thank you for watching. Again, just going to reiterate, if you have any questions, just pop them in the bottom.